Okay, this is 8.3, Modeling Periodic Behavior, and today's objective would be to use trigonometric functions to model periodic behavior. And we're talking about things in nature that change periodically. Okay, so let's have a little fun here. Graph the first period of y equals sine of x. So I hope you're to the point right now where y equals sine of x, you can visualize it. You're visualizing a periodic function, a function that has a period of 2 pi, and it oscillates between -1 and +1, and it begins at the origin. That right there, exactly, beautiful. So this is what I'm hoping you're seeing in your mind when you think of y equals sine of x. And again, some important things. Okay, the min is -1 right there. The max is +1. And this has a period of, here's the pattern, and it begins to repeat right there, and that is 2 pi. Making this pi, making this pi over 2, and making that 3 pi over 2, by the way. All right, so the general equation for any transformed sine or cosine wave. So we're going to start taking both sine and cosine, and we're going to apply transformations so we can model things in nature. Okay, so our general formula is this. So you see, this is y equals sine of x, but your first thought is, has the amplitude changed? And we use an A for amplitude, or at least part of the amplitude, because the absolute value of A is always the amplitude of my sine wave. Okay? And then we're going to multiply the x by a B. All right? And an important thing about this B right here is 2 pi divided by B is the period of our function. All right? And then we do a horizontal translation, x minus h, and that's a horizontal slide. So h represents a horizontal translation or slide. And then y minus k, this k represents a vertical translation or slide. K equals a vertical slide. Okay, now let's take a look at our general y equals sine of x, and let's find our amplitude, our period, our h, and our k. Okay, well, the amplitude is, and again, remember, amplitude is max minus min divided by 2. So 1 minus -1 would be 2, and 2 divided by 2 is 1. The amplitude of the sine wave is 1. What's the period? Well, we already talked about that, and this pattern repeats after 2 pi units horizontally. So the period is 2 pi. And B, well, B divides the period, so in this case, B would have to be 1 because the period here is 2 pi, and 2 pi divided by 1 is 2 pi. So my B is a 1, and my H is my horizontal translation. Notice how they go minus h. All right, so that means if I take x and I subtract h, that means I'm translating horizontally h units to the right. So has this been translated to the right at all? No, remember, sine begins right here at the origin, so there is no horizontal translation. And this k represents my vertical translation. So if I see minus a k, that means my sine wave would have been translated k units up. So this sine wave, again, it begins at the origin, and it oscillates between -1 and +1, so it has not been translated vertically either. So the k is 0 here, and that's why, what do I have? Y equals sine of x. All right? But now we're going to start looking at transformations. So I would like you guys to visualize the graph of y equals sine of the quantity x minus 1. So the only change here is we've taken our x, our independent variable, and subtracted 1. That's going to be a horizontal translation 1 unit to the right. So my h here, minus h, minus 1. My h is now a 1. And again, all that we'll do is take this graph and translate it 1 unit to the right. Now let's try to get that accurate. So remember our hash marks here. This was pi over 2 right here. And pi over 2 is approximately 1.57. So 1 unit to the right would be about right in here somewhere. Okay, so there we go. So let's just take this y equals sine of x, and to graph y equals sine of the quantity x minus 1, take this graph and translate it horizontally 1 unit to the right. And there you have it. Y equals sine of the quantity x minus 1 right there. Beautiful. Okay, so let's graph now the first period of cosine of x. So just like sine of x, I want you to be able to visualize y equals cosine of x. Now, remember, sine of x begins at the origin and then begins working up. Cosine has a y-intercept of 1 and then begins, as we go to the right, going down towards the x-axis. So I hope you see this in your mind right now. And by the way, I hope you might realize already that sine and cosine are nothing more than horizontal translations of each other. But we'll discover that in a little bit. All right, so let's go to work again right here. All right, remember, everything still applies. It's beautiful. So, sorry, I clicked that a little prematurely. If I'm going to take y equals cosine of x and apply some transformations, I need an a, I need a b, I need an h, and I need a k. And let's remember what all of those represent. Okay. The general equation for any transformed sine or cosine wave is, and again, the absolute value of this a will give me my amplitude. This b divides the period, so 2 pi divided by b will equal the period of my function. And this minus h would be a horizontal translation, h units to the right. And this minus k would be a vertical translation, k units up. So, in our general y equals cosine of x, again, the amplitude is, well, max minus min divided by 2 would be 1 minus negative 1, 2 divided by 2, and you have an amplitude of 1 right there. And the period is still, well, this x value right here would be 2 pi. And then b, since the period is 2 pi, and 2 pi divided by b gives me my period. The b must be 1. And this cosine function has not been translated horizontally to the right, so h is 0. And this cosine function also has not been translated vertically up or down, so k is 0. All right, now let's use this to visualize a transformation of y equals cosine of x. So now we're going to visualize and then graph y equals 2 times cosine of x. Now, what does this 2 do? It changes my amplitude from a 1 to a 2. And that means my function is going to oscillate, instead of oscillating between negative 1 and positive 1, we're going to have an amplitude of 2. So we're going to, instead of going from 1 to negative 1, we're now going to go from 2 to negative 2. So it's just going to stretch it vertically. All right, my intercepts will not change. So y equals 2 cosine of x. Try to visualize it right now. All right, my max will be 2, my min will be negative 2, and my x-intercepts will still be pi over 2 and 3 pi over 2. Here it is in bold right there. Beautiful. So all essentially that is happening here is we're taking every y coordinate in the graph of y equals cosine of x and multiplying it by 2. Beautiful. Okay. Oh, now visualize and then graph y equals 2 times cosine of 3x. So this is my b right here. B was 1, it's now 3. All right, and remember, 2 pi divided by our b will give us the period of our function. So we're going to take this period of 2 pi, and that's 1, the first period of that function, y equals 2 cosine of x, and now we're going to do a horizontal shrinkage. And the entire period will be taken care of at 2 pi divided by b, or 2 pi over 3. So the period now is 2 pi over 3. So what would that look like? Well, let me see. Pi over 2, okay, pi, so 2 pi over 3 would be right in here. So we're going to complete one period of this function in this interval from 0 to 2 pi over 3. Try to visualize that. That's a horizontal shrink. And again, this is 2 pi. And we need to take that function and shrink it horizontally. So now we complete one complete period. Look at this horizontal distance. Right there. That is 2 pi over 3. Okay, great. Now, I think we could talk about maybe some translations vertically and or horizontally. So look at what we have here. Y minus 4. That 4 is my k. Right there. Okay, so what is that going to do? Well, if I subtract 4 from y, picture it like this. I could add 4 to both sides, and if I took this 2 cosine of 3x and I added 4, wouldn't that just slide the whole function up 4 units? So what's going to happen right here is check this out. And let's just pick a point right here. And we split up exactly how far? That's right, 4 units. And that's it. So y minus 4 equals 2 cosine of 3x. You're going to get very, very good at this. Okay, now let's write this down. And this is our general sine waves. Very, very important to have mastered. So if the graphs of y equals a times sine of bx and y equals a times cosine of bx, and notice we're using capital B's here. You know, capitals versus lowercase really don't matter with period and b and even a, all right? Are translated horizontally h units and vertically k units. Then the resulting graphs have equations. Y equals, now I don't know why, maybe it's right-handed or what, but I always visualize my horizontal translation first. And so if I translated h units to the right, then this x becomes x minus h. And if I translated k units up, then this y becomes y minus k. Oh, and there's on both functions there, so right here. And now let's do the minus k for the sine wave and the minus k for the cosine wave, which, by the way, is just another sine wave. All right, there you go. Highlight that. Make sure you have your questions answered. That's very, very powerful. All right, so with those tools now, they can give you a graph of a periodic function that oscillates just like this, all right? And you can write the sine wave that represents that graph really easily, okay? So what is the amplitude? That's the first thing I think about right here. And I think about my max, because amplitude equals max, which we use a capital M for, minus the min, which we use a lowercase m for, divided by 2, equals, so the max here would be 1, 2, 3, 4, 5. The min would be negative 1. 5 minus negative 1 would be 6, and 6 divided by 2, 3. So there you go. The amplitude of that graph right there is a 3. Now the period. Well, I like to start on the y-axis. So I'm going to start right here. And how far am I going to travel before my pattern just repeats itself? And it looks like I haven't quite completed one period yet. Right there. So how far is that horizontally? Well, nothing scaled, so these hash marks must be worth 1. So 1, 2, 3, 4, 5, 6, 7, 8. So that sine wave right there has a period of 8. Okay? Now, that implies, well, if I have a period of 8, I'm going to use that to find my b in my general function. So I'm going to say 2 pi, the general period of a sine wave, divided by the b has to equal 8. Now let's just solve that for b. So that implies b would equal, and if you were solving this equation for b, you'd multiply by b and then divide by 8. So b equals 2 pi over 8, which I would write as pi over 4. All right. So this implies the sine wave is a translation of, so right now I'm just going to put in my amplitude and my period business, and then we'll worry about horizontal and vertical translations. All right, so my first thought is, what is my amplitude? And we said the amplitude was 3. So let's put a 3 right there. All right. And then we said our b was pi over 4. So we're going to take this x and multiply it by what? Pi over 4. And we can do that with sine or with cosine. Exactly the same thing. So the amplitude is still 3 and the b is still pi over 4. Now, let's think about our horizontal and our vertical translation. Let's use cosine first. And on problems like this, I tend to use cosine because it's easier for me to see the distance of the horizontal translation with cosine. So before we talk horizontal, let's say the axis of the wave. Now the axis of this sine wave right here is simply the horizontal line that goes right through the middle of the function. So let's see. I mean, the range of this function is what, 6 units? So wouldn't that horizontal line be nothing more than y equals 2 right there? Guess what? That is my k. But let me show you why. Okay, there's a formula for the axis of the wave, which gives us our k, that is very similar to our amplitude formula, except it is max plus the min divided by 2 equals, now take a look here. Max was 5, the min was -1. 5 plus -1 is 4, and 4 divided by 2 would be 2, and that's why we have this axis of the wave is the horizontal line, y equals 2. And again, that's my k. Now the horizontal translation, and this is why I love to use cosine. So cosine typically starts with a max at the y as the y-intercept. So, but this max, it looks like we translated how far horizontally right there? Well, let's look down here. 1, 2, that looks like the x-coordinate of that point right there would be 3. So it looks like we translated 3 units to the right. 3 units to the right, look at that. Now, let's take this cosine function, y equals 3 cosine of pi over 4x, and apply both our horizontal translation and our vertical translation. And that's nothing more than what is the h and k. So if I'm going to do horizontal first. If I translate 3 units to the right, that means I'm going to take this x and subtract 3. And then if I translate 2 units up, I'm going to take this y and subtract 2. And there is the cosine function that represents the transformation of y equals cosine of x to get this beautiful graph right here. Now, wouldn't it be cool if we could also do this in terms of sine? And guess what? We can. All right, so let's try this with sine now. Now, the beauty about this is, remember, sine and cosine are nothing more than horizontal translations of each other. So the axis is still y equals 2. Okay, the horizontal translation is the only thing that's different right here. All right, and instead of translating 3 units using cosine, it looks like we took sine and we only translated horizontally 1 unit. So 1 unit to the right. And now let's set up the same way. Now look at so far, the only difference is instead of cosine, I am using sine, which we still have the same amplitude. We still have the same period, giving us a b of pi over 4. All right, and you know what? The only thing that changed was the horizontal translation. We slid 1 unit to the right, so I'm going to take x and subtract 1. All right, the axis is still 2, so my k is still 2. So I translated vertically 2 units up, so I'm going to go y minus 2. And these 2 equations are equations of the same graph. You're looking at it. One is in terms of cosine, and the other is in terms of sine. And these are both called sine waves, even the one in terms of cosine, because cosine is what? That's right, cosine is a sine wave. Cosine is just sine that has been translated horizontally. That's big stuff right there. And we're going to get better and better and better at every piece of this. And you're going to become experts. I promise you. All right. So that leads to a very cool story problem. And these story problems always look like this. All right. You know, the tides are periodic. All right. So a big application of periodic functions is there are harbors that, you know, the tide goes up, it comes down. And there are some very big ships out there that at lower tides, they cannot get into the harbor because there's not enough water. My father, when I was a teenager, owned a very big fishing boat. It was a 56-foot fishing boat. In fact, it was called the Sea Sprite. All right, and we usually fished out of Ilwaco, Washington, and there was plenty of room to get in and out. But every once in a while, we'd come up north, and if we went into the small marina in Ocean Shores, we could only get into that marina at certain times during the day when the tide was high enough. So this problem is written about that boat right here. So the depth of water at the end of a pier varies with the tides throughout the day. Today, the high tide occurs at 4:15 a.m. with a depth of 5.2 meters. All right, so I'm going to plot that point. My input is time, and that would be 4:15, and my output is depth in meters, which would be 5.2 meters. So 4:15 would be, think about that as a decimal in hours. That would be 4.25 hours. So 4.25 would be about right here, and then I've got to go up to 5.2. 1, 2, 3, 4, 5, 5.2. About right in here. And this does not have to be perfect. This is just a rough sketch right there. And again, what are the coordinates of this point? Well, I'm going to write 4:15 a.m. as 4.25 hours. And then the depth of 5.2 meters, 5.2. High tide right there. Beautiful. Now, the low tide occurs at 10:27 a.m. All right, now that's going to be a little tougher, 10:27. 27 minutes is what decimal of an hour? So let's take 27 and divide it by 60. You guys punch this out with me and double check. 27 divided by 60. All right, I'm getting 0.45. So I'm going to write 10:27 a.m. as 10.45 hours. So let's get that into this picture here. 2, 4, 6, 8, 10. So that'd be 12. So 10.45 would be about right in here. And what is my depth? 2. So I go up 1, 2. So I'm going to put this point about right here. Does not have to be perfect. This is just a general sketch. Oh, look at that. And again, remember, what was our input T? 10.45. And what was our output? 2. Okay. Now, you guys again know that tides are periodic, right? And like to get from high tide to low tide, that's always a little over 6 hours. So I'm going to use periodicity, and I'm just going to translate both of these points approximately 12 hours to the right, a little farther. All right. So, and again, tides are periodic, so just take this point and slide it a little more than 12 hours to the right, and do the same with this point down here. And you have a scatter plot now for a beautiful sine wave. So let's draw our sine wave. There it is. Look at that. Beautiful graph. And we have that graph understanding that tides are periodic and they only gave us 2 points. Okay, now find a trig equation that models the depth of the water t hours after midnight. Well, we graphed it right there. So now what's the equation? And it's just like the problems we've already done now. Okay? First, amplitude. Well, what's the amplitude? And you guys know amplitude is max minus min divided by 2. So that looks like I put the formula there. So I'm going to go uppercase M for max. Oh, I didn't. I went right to it. Okay, remember now. Max minus min divided by 2. All right, so I'm going to get out my calculator right now. And I'll put it all. Oh, I'm running out of battery on my calculator. I better get this charging today. So what was the maximum depth? 5.2 minus, and what was my min? 2, which of course is 3.2, and then divided by 2. And let's put that all together here. So I had a 5.2 minus my min 2 divided by 2, and that equals, and my calculator is saying, I better do that again, 3.2 divided by 2, what would that be, 1.6? 1.6. So the amplitude of this function is 1.6. That means the distance between the min and the max would be twice that, or what, 3.2. Anyway, here we go. What's the period? All right, now I only have the coordinates of 2 points right here, but do you guys realize that going from the max to the min, that horizontal distance would be 1/2 of my period? So how about I find this horizontal distance right here by just going, what, 10.45 minus 4.25? So let's get out our calculators again and go 10.45 minus 4.25. And that gives me a 6.2, all right? But now I've got to multiply that by 2 to get 12.4. So guess what? The period of this sine wave right here would be 12.4. All right, great. And now can't we use that to find the b in our sine wave function? All right, so we know that b always divides the period of a typical sine wave, which is 2 pi. So 2 pi divided by b then would have to equal this 12.4. All right, now let's solve this for b. And I'm going to take this to the next level here, you guys, because, you know, I don't like to see decimals within fractions and things. And, you know, you could punch this whole thing out and give me a decimal approximation, but I'd like you to go as exact as possible. So let me talk you through this. Well, I'm going to multiply both sides by b and then divide by 12.4. So I want to know, what is 2 divided by 12.4? So let's punch that out on our calculator. 2 divided by 12.4. Okay, and I'm getting a really ugly decimal, but wouldn't it be great if my calculator would make that into a fraction for me? So I'm just going to go math fraction. And look, I'm getting 5/31. So let's make sure we picture this right. The b came over to the right, and then I divided by 12.4, and I said 2 divided by 12.4 was 5/31. That means b would be 5 pi over 31. There you go. Look at that. That's a nice clean answer right there. And again, if you give this b to me as a decimal approximation, I mean, that's really okay, because did we approximate? I don't know. Those were exact, weren't they? So maybe we'll just leave this exact right now, but you can use a decimal approximation for this b if you're more comfortable, all right? Now, let's do our general sine wave, and I like to use cosine because I can see the horizontal translation really easy here. So remember, all right, what's the amplitude here? It is 1.6. So let's put a 1.6 right here for our A. All right, and then our B is what we multiply our independent variable by, and that would be 5 pi over 13. Now, we're almost there. All we have to do now is account for our horizontal translation and our vertical translation. So, let's go to work right here now. I might probably crunch some numbers out here first. Like, let's think about this. I do know the horizontal translation already, but let's see. Oh, I did do that. So let's talk about that before I push the button. All right. Do you guys agree? We're using cosine. Cosine usually starts with a max as a y-intercept, but that max looks like it has been translated how far? 4.25 units to the right. So I'm going to have right here a t minus 4.25. There's horizontal. And then the vertical translation is nothing more than the axis of this wave. All right? And what is the axis? Start memorizing these formulas. It's the max. I don't have the formula there. I'm sorry. But it is the max plus the min divided by 2. And the max is 5.2. The min is 2 divided by 2. And what does that equal? Well, 7.2 divided by 2, that'd be 3.6. So y equals 3.6 would be the horizontal line that goes right through the middle of the sine wave right here. So my cosine function has been translated 3.6 units up. Y minus 3.6. And that is the perfect equation for that story problem right there. Okay. Now, we could do this with sine too, but hey, I've got a good tool right here. I think I'd just keep it with cosine. All right, so, looks like they're going to ask us more questions. Okay, so let's make sure we answered A. Find a trig equation, and it doesn't matter if you use cosine or sine. The only difference would be the horizontal translation. It'd be less than minus 4.25. It'd be, I don't know, approximately right in here somewhere. A little bit over, what, 2? Okay, but anyway, we've got it. So now we've got to find the depth of the water at noon. Well, since we have this great equation right here, why don't we put it into our calculator? Y sub 1. So I'm going to go y sub 1, and to put this in my calculator I have to solve for y, and that's why some people like to put, instead of the minus k, they go y equals and they have a plus k over here. So let's just take our expression on the right and add 3.6. And you want to be very careful putting these in. Careful with your parentheses and so forth. You got to think like your calculator. So, and let's see. I don't know. It is trig. 5 pi over 31. I think we need to be in radian mode. So let's go mode, and let's go. I'm in radians right now, so let's all go radians. All right, and then go y sub 1 equals 1.6 cosine of parenthesis, and then put in your 5 pi over 13, 5 second pi divided by 13. All right, and then another parenthesis with we have to use an x minus 4.25, x minus 4.25, and close that quantity x minus 4.25. Let's close our cosine of what? So another parenthesis, and then to that let's add the 3.6 plus 3.6. all right, so I'm sorry you can't see me punching that out, on this video, but we have most of it I could fit right into there. So make sure you put this in very carefully. And if you did it, now you probably want to change the window to match this situation, because what good would it be to put this on a typical trig window? So let's think about our window now. And look what I did right here. All right, well, I'm going 0 to 24 hours, one day right there. So midnight to midnight, all right? And then I scaled my t's by 2's. Look at that, x scale of 2. And then it looks like I did a y min of -1, so I could see the horizontal axis clearly. And I did a y max of 6 because of that max here, 5.2. And I scaled my y-axis by 2 just like I did here in the picture. All right? And then anything below that, I don't mess with that stuff. All right? Now, if I hit graph, that's what I should be looking at. So everybody hit graph now and see if you have the same picture we have. Hey, whew, I have it. Okay? All right, awesome. So let me just clean this up one more time here now to make sure. Okay, I went 0 to 24 with a scale of 2, and then I went -1 to 6. Uh-oh, I got a go-to error. I see, delete. -1 to 6, and those are scaled by 2. Give me a second to catch up with you guys on my calculator, please. -1 to 6, scaled 1. That should be the perfect graph. Okay, now let's play with this a little bit here. Okay, f of 12 equals second. Okay, and I'm going to go second calc and find that value. All right, so x equals, and I want to put in a 12 for my x, and look at what I am getting right there. Okay, this point right here, and I'm getting a 2.4686692. All right, and so I probably rounded that 2.5 meters. All right, now finally, the sea sprite needs at least 3 meters of water to moor at the end of the pier. During what time period after noon can it safely moor? So you guys, what I probably want to do is put a horizontal line into this picture of y equals 3. There it is right there, right? And the sea sprite, my father's boat, needs 3 meters to moor safely. We don't want that hull hitting the bottom or a rock or something like that. All right, so it looks like afternoon, I'd be talking about this interval right in here. Okay, so there it is right there. All right, and you know, I should have put open dot on both ends of these right here because I want to be above 3 meters. What did it say? At least, so the equal is appropriate, but I think I'm going to find this x value and I'm going to round what up. And I'll find this x value, and I'm going to round down, okay? So there's my graph right here, and it looks like I got a 12.791385, and then I'm going to find this point right here, and you guys know how to do that. That's just zoom intersect. We're finding where our graph intersects with that line y equals 3, and I got a what? 20.508615. All right, now let's clean those up a little bit here. So 12 point, and I'm going to make that into, hours and minutes. All right, so look what I did here. 12 what p.m. to 8 what p.m. All right, so let's figure that out now. So I put the decimal part of my hour right there, and I got 47.4831. So what do I want to do? I want to round that one up. So I'm going to go 1248. It's okay for my father to dock his boat. All right. Now this one is 30.5169 right there. All right. So how about we go 30, we're going to round this one down. All right. So how about from, and that was military time, 20 hours. So wouldn't that be 8:30? 8:30. And that's when it's safe for us to moor the Sea Sprite in the marina at Ocean Shores. Just that time right there. Let's keep the boat safe. I hope you guys enjoyed that problem as much as I did. That's a really cool problem. And if you have questions, let me know. We're going to be doing more and more problems like this on the review. Make sure you have that y minus k equals a sine of the quantity b times the quantity x minus h down. All right, and know what all of those mean. Amplitude, your b divides the period, your h is your horizontal translation, and your k is your vertical translation. That's going to go a long way. So let's do these problems. Page 313, 1 through 7 odd, 15, and on 15 all I need you to do is write the equation, okay? And then 19 and 20. I'm wishing everybody a great day.